So for Science 10, we're going to be using the Arrhenius definition of what an acid and base is. And as you work your way through school, you'll learn different scientists created different definitions of what an acid would be. Eventually you use Bronsted-Lowry, and in post-secondary you may use Lewis. So Arrhenius defined an acid as any substance that can produce hydrogen ions in solution. Okay? And when we say solution, unless I tell you a different solvent, it's always water unless otherwise said. Okay? So in solution means in water. Okay? Okay? So there are these few molecules that you put them in water and the water is able to rip off an H+. Okay? It's rare. Do not assume that every time you see an H+ or sorry, a hydrogen in a molecule can come off. But there's a few cases and we'll go through those. You don't have to memorize what acids can do this. You know, you have lots of tables on your sheet that tell you. So this booklet for Science 10 and your orange Chemistry 2030 data booklet has a huge list of acids and bases. Okay? So don't memorize, but be aware. Okay? So, and it's hydrogen ions. The reason you get similar properties from all kinds of different acids is they're all producing this common ion. Okay? And that's why you can have things like pH paper that you can use this for any acid because of that commonality. Okay. That H+ in solution tends to give certain taste properties, and for cooking and food that might be beneficial. Acids tend to have a tangy flavor. And it tends to tweak those sour taste buds. Okay. We're going to go through some examples of acids, and when you put them in water, we get these acidic solutions. So hydrogen chloride, which all by itself would be a gas. At room temperature, room pressures, HCl, hydrogen chloride is a gas. You put hydrogen chloride in water, or you bubble it through water, and we get the acidic properties. Those and future ones. Okay? You get that because it's one of those molecules that can produce H+ in solution, Arrhenius' definition. Okay? So this is gas, you bubble it through water, and now it's surrounded by water, the solvent. And you get Cl- chloride. Another really commonly used acid, sulfuric acid, starts as H2SO4. You put it in water, and one of those H's totally comes off. Okay? You get H+, okay? And then everything else that's left over. Okay? The second H is left over, the S, the O, 4 of them. That has a minus charge, and that's surrounded by water. Okay? Now, because we're getting ions, we have electrolytes. Okay? A solution, a chemical, a molecule that you put in water that makes an acidic solution, you would get the connectivity light turning on. Okay. A few other examples that are a little bit more complicated. Ethanoic acid. Its chemical formula is CH3COOH. And I'm picking this one example to highlight a whole bunch. As a student, when you see this COOH, that last H can always come off. And there's a whole bunch of acids that fit in this category. Actually, I'll leave out the structure. You put that into water, this would be a liquid all by itself. That end H comes off. The C, the H, the 3, the C, the O, all that first part stays. So it's only ever this H that comes off. And that's a really common acid. You could, the common format is to break them out, and the reason you see every textbook and every source break them out, I think, is to emphasize to the reader that this is an acid. That this O is connected to the C, and the second O is also connected to the C. So I think it's just convention is the best answer. There probably is no answer. It's just the way everybody does it, and it's to emphasize the COO format. So convention, not a great answer, but that's what it is. Okay. Please don't ever try to remove these H's. It's rare that H's come off, but this format. Okay. I know some of you may have consumed this particular acid. When you put that acid in water, that's vinegar. 5% ethanoic acid in water, and you can buy it at any grocery store as ethanoic acid, or it's referred to as vinegar. Okay. Okay. Again, because of the commonality of all of these H pluses always being formed in an acid, we can do some litmus paper tests, because these will respond to that H plus regardless of the acid, or we'll talk about bases later, and they respond to an OH minus ion. So if you have blue litmus and you dip it into an acidic solution, this guy responds to basis. You won't get any response with blue litmus paper. So blue litmus, sorry, I said that backwards. Blue litmus does respond to acids. It is the one that changes color. Okay. Blue litmus will change red, okay, in an acid. So this is the acid section. I'm not writing in an acid, but that's what I'm referring to. Okay. Red litmus, okay, will stay red in an acid. Okay. The main message for students to take away from this is, in an acid, these are going to either turn red or stay red. Okay, so think of acids and red, and you'll be okay. There's another sort of mnemonic I'll mention after I talk about the bases. Acids, these papers either stay red or turn red. Okay. So these are just binary tests. pH paper. How many used pH paper in the past? Okay, good, a fair number. So these give you like a 1 pH unit range bit of information. Litmus is just sort of yes or no. Okay? If it changes, it tells you something, or it stays the same. Okay? We will use both, but we use these a fair bit in high school, the litmus papers. Okay? One last acid I want to talk about. Carbonic acid. And this is more on the environmental side of chemistry. Okay. Now, carbonic acid is quite useful to understand because of how it's made. Water, that's everywhere, reacts with carbon dioxide that is in our atmosphere, has always been in our atmosphere. There's a bit more of it now, but it's always been there. That makes carbonic acid. And since our planet has acted the way our planet has, we've been getting carbonic acid made in the atmosphere and in our any water-based environment. And this carbonic acid follows Arrhenius' definition of an acid. Carbonic acid will lose one of those H's, keep the second, and make an anion. And this first reaction, the fact that water reacts with carbon dioxide naturally, this isn't something man has done. Okay? It has nothing to do with the Industrial Revolution. This is totally separate from the greenhouse effect. Don't make any of those connections. This is natural. Okay? But this natural process is why rain is acidic, okay? Because of this process. Any rain anywhere on the earth is going to be naturally a little bit acidic. Okay? Acid rain is when more chemistry happens. You get water reacting with nitrates and sulfates, and you make sulfuric acid in the atmosphere, or you make nitric acid in the atmosphere, and the rain becomes even more acidic. Okay? But just if you go outside and you collect some rain and you measure its pH, you're like, oh, it's 6. That's perfectly normal. It actually should be a little less than 6. Somewhere in the 5s is normal. Okay? Rain is not 7, okay, because of this process. Okay? So that's your earth science lesson of the day. Okay? So that's acids. They make H+ in solution. Let's talk about bases for a second. Okay, and this whole course uses Arrhenius' definition. And this is, a couple hundred years old, this definition we're using. Okay, Arrhenius defined a base as a substance that produces hydroxide ions in solution. Okay. I'm not going to write it a second time, but in solution means in water unless you're told the solvent is something else. This is one of those polyatomic ions that's on your sheet. You don't have to memorize. If you forget what it is, you go look it up. And hydroxide ions, or OH, and the O and the H together have a negative charge. It is one extra electron. I don't encourage you, please don't taste any of the bases in the lab. But if you did, they tend to give a bitter taste, and they're very corrosive. The Arrhenius ones are incredibly corrosive. Now, I'm getting old and nobody's seen this movie anymore, but has anybody seen the movie Fight Club with Brad Pitt in it? A couple hands. 10 years ago, everybody would put their hand up. It's a little bit of a disturbing movie. Brad Pitt has, some strong mental health challenges, split personality. In the movie, he puts sodium hydroxide, it's called lye. It's actually this exact chemical that I have here on the back of his hand, and immediately starts burning his skin. It starts bubbling, scars him permanently. Okay? Bases are really corrosive, okay? Particularly when you put a 100% solid on my skin, and then the moisture in my skin starts dissolving it. It's going to eat your skin, okay? Now, you'll handle it. You're never likely to use it in the pure powder form. If you get it on your hand, you don't panic. You just want to wash it off your hand right away. You wouldn't want to get a solution of this on your hand and leave it for 2 hours. That could give you a pretty good burn, okay? You don't even need soap, you just need some water to rinse it off, okay? But anyway, bases are very corrosive, okay? If a student is using a strong base and the student's like, why are teachers bugging me to always have my safety goggles on? You do not want strong bases, which we use regularly, getting them splashed in your face or your eyes. Some examples of bases. So sodium hydroxide is this exact stuff. I'm going to demo it in a second. It is a solid in its ionic form. We see that metal and a polyatomic. So we got 2 ions here. We've got an ionic compound. I put that in water and make a solution. The sodium ions separate from the hydroxide and get surrounded by water, AQ, and we get what we're really after, hydroxide ions surrounded by water, and that's what makes the solution basic. Sodium part doesn't really matter. The sodium part isn't corrosive. Our oceans are filled with sodium ions. The Bow River probably has a fair bit of sodium ions. It's that we're concerned about. Okay? Calcium hydroxide is another Arrhenius base. Okay? The only difference here is because calcium is 2+, there's 2 hydroxide in that formula unit. So it's going to make double the amount of hydroxide when everything comes apart. Okay? And we're really going to focus on this balancing next week. Okay? So we're going to get hydroxide again. But because of this subscript 2, there's 2 of them stuck to the unit. When everything comes apart, we put a 2 in front. Okay? This 2 is sort of referring to that everything is together. Here, all these hydroxides are separated. Okay? So this 2 doesn't mean the 2 are stuck together. It's just referring to how much there is. Okay? If you were counting up all the O's, there's double the amount of hydroxide compared to the amount at the start. Because when it comes apart, it makes 2 units when it falls apart. Okay. These guys, you know, can have some effects on litmus paper. Here, the blue litmus, when you dip that into solution that's basic, is going to stay blue. It's the red litmus that's going to change. Now, for myself, students need to come up with some system that's going to make sure you remember what this blue and red litmus does. For myself, I just remember base and blue. Okay? This doesn't have to be your way, but it's my way. I remember if it's a base, the red is going to turn blue and the blue is going to stay blue. And then I just remember the acids are the opposite. Okay? And that's how my brain remembers this. Base and blue. Okay? So I put these in a base, blue stays blue, red turns blue. Okay? For acids, they all turn red. So it's the opposites. Once you remember base is blue, then it's easy to remember acid has to be the opposite, has to be red. The pH scale is something that as you work your way through high school, you'll learn more and more about it and add a bit to the complexity. So you're probably used to 7 being a neutral pH. And that statement is actually true at 25 degrees Celsius at standard room temperature. If a solution was like 90 degrees Celsius, that would not be true. But it's true at 25, and that's where most of our chemistry is done at. Typically, you'll see 0 put at the bottom end. Is that what you're used to? It keeps going. It doesn't stop at 0. It rarely goes below 0, but it definitely can. If you have a lot of solute, a lot of chemical put in water, the pH can go sub-0. Okay? Typically, it doesn't go below 14, but it certainly can. If the base is concentrated enough, if I put enough pellets in here, enough sodium hydroxide, I could get the pH above 14. but I would have to put a lot in. Often it's not possible to put that large amount of solid base in to get it to dissolve. Okay? But please don't think that 0 and 14 are limits. They are not. Okay? They're common boundaries. Okay? We have our acidic pHs. Okay? Our acids make acidic solutions. Okay? And we have our basic pHs from 7 and above. Okay? Okay. If we look at what blue litmus does, and we're going to look at red litmus in a second. Okay. These react with either the H plus or the OH minus in solution. Okay. Now I put these arrows going away from 7. With the above 7 in the basic solutions, the further you get above 7, the more and more hydroxide you have. And the more and more basic it gets, and the more and more corrosive it would be. With acids, as you go lower in number, away from 7, there's more and more H plus, and the effects of acids amplify. And certainly around 0, 1, 2, or negative, they're also very corrosive. Okay. So you're going to help me with the colors. Blue litmus, what's blue litmus going to do in an acidic solution? Turn red. Yeah, the acids, you just remember acids and red. So bases are blue, acid, you're just remembering red. So blue litmus is going to turn red. I've lost. Okay. The red litmus, we're remembering red for acid, so this one's going to stay red. Okay. Now there actually has to be a sufficient amount of H plus in order to change color. So you'll actually find you only get these working from like 4 or less. If you're at 6.9, there's not enough H plus to get these to change color. So the change, blue litmus turns red in acidic solutions, but you have to have enough H plus. If you're just barely acidic, they're going to give you a false reading. It's not going to change. Okay. With the basic solutions, it's around 8. They'll change or stay the same. Blue litmus, okay, basis, you're remembering blue. So blue litmus is going to stay blue. Red litmus will turn blue. But really close to 7, 6.5, 7, 7.5. Neither of them are going to change color. Just because there's not enough of those ions to cause that color change. So lastly, we're going to do our demo, but we're going to talk about naming acids on our next slide. So again, so we're just naming binary acids. The first element has to be hydrogen. We need hydrogen or it would not be an acid because we have to get that H plus. So we're going to be seeing H and a non-metal. We're not going to see any metals here. An example, hydrochloric acid is one of the most commonly used acids. Binary acid names always follow the following format. they're going to be hydro something that connects to that, whatever element is the second element, ic acid, where the blank contains the nonmetal compound name with the "ide" removed. And I'll go through 3 examples. The first one, doing the acid name for our hydrogen chloride when we put it in water. Now, I added the word aqueous in front. You'll see textbooks or certain sources put that in. All the word aqueous means is what's after it is in water. That's it. It doesn't show up as a symbol. It's just, you tell us, you know, if you're writing it in formula form, you got to put AQ afterwards. Or this is now in water. It's not by itself. Okay. So I could call this aqueous sodium hydroxide because it's in water. So I have to start with hydro, because this is a binary acid, hydrogen and one other thing. The chloride, I'm going to drop the IDE. So CHLOR. I shouldn't have put a space in. So drop the IDE, and now I'm going to go ic space acid. So when I put hydrogen chloride in water, okay, we now have made hydrochloric acid. My second example would be if you put hydrogen sulfide into water. And you wouldn't know how to predict whether this is an acid or not. Okay? That's not the skill you need to learn. You'd have to be told, okay, this is an acid. What is its name? So we're going to start with hydro again, because we've got 2 different elements. Okay? Your big hint that you've got 3 or more would be 8 or ite here. If you see 8 ite, then it's one of those polyatomics. We're seeing ides, so it's just 2. Hydro, SULF, I'm dropping the ide, ic acid. So hydro, sulfuric, I forgot the UR. I should have had it there. Last, hydrogen bromide. I just took out the aqueous this time. You might see the word aqueous there, or you might be asked, what's the name of this compound when it's put in water? You put hydrogen bromide in water, and you make hydro, brom, drop the IDE, add ic, acid, hydrobromic acid. Now, on your formula sheet, you get this reminder. So you don't even really have to memorize that. You just have to know when to apply it. You have to recognize it's binary, maybe check your data sheet, and follow that format. Next year, you'll lose that on your formula sheet, but for Science 10s, you get that. And again, you've got to copy the formula sheet on D2L if you want to print your own. Okay. Last is, what if you have H with nitrate or some polyatomic, and it makes an acid, that H comes off? How do you name those? So the acid is going to get its name just from that polyatomic ion component. We're going to lose that hydro in front. And that's the big difference, and the first thing a student should notice if you're looking at a name. If it says hydrochloric, it's H and a Cl. If it just says chloric acid, you know it came from a polyatomic. Okay? No hydro in front. Go look at your polyatomic sheet to figure out what it is, what it came from. So we got some ending changes. If what was put into solution, if the polyatomic ended in 8, you're going to switch the ending to ic space acid. If the polyatomic ended in ite, you're going to switch it to us at the very end. The ite's going to disappear. Us will take its place, space acid. What comes in front of the ic and the us is just whatever is the front part of that polyatomic name. No hydro. Now the 8 and the us are very old terminology. The history of this naming, and it's just humans came up with a name and a system. The 8 comes from the polyatomic with more oxygen. The us, or the ite, comes from the one that has less oxygen in the polyatomic. So one example that's come up a little bit in our notes is NO3 minus and NO2 minus. The NO3 minus, the more oxygen, is a nitrate. So NO3 minus is nitrate, NO2 minus is nitrite. Okay? The 3, the more 8, the 2, the less ite. Okay? Now occasionally you have 3 or 4 oxygen containing compounds. Okay? And then you'll see these terms. So the 8 is more, the ite is less. But if there's 4 versions, the one with the most, the highest, would be per something 8, and then 1 less oxygen 8, and 1 less ite, and then the smallest amount of the 4 hypoite. This is largely, you're going to see these names in your booklets. You don't have to memorize these, but you have to know how to use the tables that are here. Or you might see a name that's hypochlorite. You're like, why the earth are they doing hypo and an ite? The reason is there's 4 options. Maybe the ite has 2 O's and the hypoite only has 1. Okay? The 8 would have 3 and the per would have 4. Okay? But there's no rule that says the per is always 4. The per just has the most, 1 less, 1 less, 1 less is the system. Again, this would be probably really hard and would just be a lot of memorizing if you didn't have your data sheet. But maybe take a look tonight at that formula sheet and you realize all, these bits are all summarized there. You're just applying. So I'm going to go through some naming examples and then we're done for today. Sorry, I got to do bases super quick. Okay. So first, hydrogen sulfate. So we're not going to include the hydrogen in the name. Now with sulfur, because it sounds really bad, the UR is put back in. And then with, we're going to drop the 8, and the 8 switches to which of those 2 endings? The us or the ic? The ic. Okay. The 8 turns into the ic space acid. My second example is the lower one. The ite has less O in it. Okay. We don't include hydrogen in the name. We only use that when there's binaries. Okay. Sulfur, we keep the UR just for pronunciation reasons. Okay. So I added the UR in even though it wasn't there. Okay. That's the lower one, so I add OUF. I'll just write. Two more. Okay, we got an 8, so we're going to drop that 8. Okay, we also have them putting in the hydro part. Okay. I'm going to drop the 8. 8 goes to ic. Chloric acid. Now this creates two names that are really similar. We have hydrochloric acid, H and Cl. Okay. Chloric acid is coming from this chlorate. Okay. So you've got to go and look up what chlorate would be to get its name. Okay. Last example of the day, hydrogen nitrite. Okay. So I'm not going to put the hydrogen. I'm going to switch that ite. Ite goes to us, space acid, nitrous acid. So just, you get a question about naming acids, just slow down, flip to your formula sheet, and just keep the binary separate from the poly. And it should go fairly well. Okay. Quickly, just doing acid naming. Okay. There's no change in the name. Okay. We don't add anything. We don't change anything. Okay. I just want to identify where you're going to see these Arrhenius bases. They're going to be a group 1 cation plus hydroxide. So lithium, sodium, potassium, all the way down to francium, those with OH minus, or you'll see group 2s. Okay. Calcium, beryllium, magnesium with hydroxide. Those are your Arrhenius bases. Okay. So first example I did was calcium hydroxide. I'm not quite done yet. Okay. Now calcium is a group 2. So when it's an ion, it's 2 plus, and hydroxide is always 1 minus. Okay. It's on your formula sheet. You don't have to memorize that. If you forget the charge of hydroxide, check at the very top. 2 plus and minus 1 don't balance. Lowest common multiple is 2. So we want plus 2. We want minus 2. So I have to bracket that polyatomic and put a 2 after it. But its name is just calcium hydroxide. It doesn't change because it's a base or you put it in water. It doesn't have a different naming system. Same with lithium hydroxide. Lithium is a group 1, so it's plus 1. We've got hydroxide again, minus 1. That's balanced, no subscripts needed. That's lithium hydroxide. You're seeing your acids are coming from molecules. Okay. Your acids are coming from groups of these guys with an H. Okay. H is not a metal. It's way over here on the metal side, but it's not a metal. It's over here because it has 1 dot in its electron dot. Everything here has 1 dot in its electron dot diagram. So that's why it's over here. You do see periodic tables made that have hydrogen here. You also see periodic tables that take helium and put it here, because helium has 2 dots in its Lewis dot, and so does beryllium. Okay. But you really have to, when you see hydrogen, think of it maybe over here more in terms of its properties. Okay. It's sorted by its electron dot. So your acids are compounds, they're molecules. Your ionic compounds, with hydroxide, your ionic compounds are making your bases, the ones that contain hydroxide. Okay. Some questions to take a look at to wrap up today.